All right, so this is the second area recap video for AP Calculus. This video, it's not really going to be much of a recap because we're really going to be discussing things that we haven't discussed previously in any of our other wonderings and activities. So we're going to start with rules for definite integrals. And I'm going to talk through each of these. A lot of them kind of make logical sense if you think about it, but some of them we'll want to kind of think about and make sure that we fully understand them. So the first rule is the order of integration. So notice that we're integrating in the left-hand side of the equation from b to a function, and then on the right-hand side of the equation, we're integrating from a to b, the same function. So if you think about it, area under a curve, if this is my curve here, for example, from a to b, well, integrals are directional. So if I'm going from b to a, it's still going to be the same amount of area under that curve. It's just going to be going in the opposite direction. So when we change the order that we're integrating in, it's still the same integral value. It's just the opposite sign of it. So for example, that graph that I drew, if there's a total of 4 square units of area under there, then the integral from b to a would be -4. Okay. The second one, the zero rule, that one kind of makes logical sense, again, if you think about it visually. If we're integrating from a to a for any function, well, those boundaries tell us how wide our space is that we're finding the area under. But if we are going from a to a, there is no width. So if you think about the basic concept of these areas being kind of a base times height issue, the base would be 0. So it's actually kind of irrelevant whatever the function or the height is, because the base width is 0. So if the beginning and the ending boundaries are the same, then your answer is always going to be 0 for your integral. The third one is the constant multiple rule. If you're integrating and you have a constant times your function, you can leave it inside the integral, but sometimes it's helpful to just pull the constant out in front, integrate the function, and then worry about multiplying the constant at the end. And that definitely applies to when we start doing integrals algebraically by hand more than anything else. It also applies to negative signs. You could pull those out in front, worry about integrating, and then slap the negative on at the end, because that's kind of like having a constant of -1 in there. The sum and difference rules, if you're doing an integral of multiple functions and they're being added and subtracted, sometimes it's helpful if you can split them up and worry about each function individually and do its integral, and then worry about whether you should be adding or subtracting them after that fact. It just kind of makes it a little bit easier if you can go piece by piece through the whole expression rather than trying to do everything at once. Number 5 is the additivity rule, and that says that if you have an integral from a to b for a function and an integral from b to c for a function, then that would be the same as going from a to c. So again, we can kind of visualize that. If we're going, here's a, here's b, here's c. Well, if I find the integral from a to b, it's going to be that much. And then if I find the integral from b to c, it's going to be that much. But if I just went straight from a to c, it's the exact same amount. So I can chop it up, or I can just leave it as straight from a to c. Sometimes it's helpful to chop it up, and that will just depend on the situation. A lot of times it's visually. When it helps, if we're trying to calculate the area geometrically, then you can chop it up into the shapes that you see. Like maybe the first part is a square, but then the next part is a semicircle, and then the next part is a triangle. You can kind of do those sections piece by piece instead of trying to do them all at once. Then we have the max or min inequality, and I'll be honest, we don't really use that all that often. So what it's saying here is that if I have some function, we'll just make it be this, from a to b, and if I don't quite know what the exact area is under that function, for whatever reason, maybe I don't have an equation for it, or maybe it's not very geometric and I'm trying to do it with a graph, who knows what the reason may be. What I can do is I know that the smallest possible answer for the integral would be the smallest or the shortest rectangle that I could make from a to b. So that would be using the minimum y value, which would come from here. So I know at the very least, the area under that curve would have to be the amount under that blue rectangle. At the very most, it would be whatever my maximum y value is, and the area of that rectangle from A to B. So what really all that does is it kind of helps you maybe narrow down your multiple choice possibilities for what the exact area might be under that red curve. It's not entirely helpful, to be honest. And then the last property is the domination rule. And so what that says is that if you have two functions, and if they are graphed along the same interval, so here's f, and then here's g, notice that f is always greater than g. So all I know from that is that whatever the integral is for f from a to b, its value is going to be more than the integral for g from a to b. But I only know that if f is always above g. If they kind of crisscross at certain points, then I can't use the domination rule. So only if f is above g at all times does the domination rule apply. Okay, so using some of those rules, we just have some random information here about two functions, f of x and h of x. We know that the integral from -1 to 1 for f of x is 5, and then the integral from 1 to 4 for f of x is -2, and then the integral from -1 to 1 for h of x is 7. So based off of those three pieces of information, we want to find these other 6 integral values. So A wants us to find from 4 to 1 for f of x. So I go up and I look at my information, and I notice that I see 1 to 4. 1 to 4 is -2. So if all I do is reverse the order, remember that's the order of integration. So all that does is change the sign. So it would be -2 or +2. And then B wants us to find the integral from -1 to 4 for f of x. Well, I know the integral from -1 to 1 is 5, and then from 1 to 4 is -2. So if I piece those together using the additivity rule, then that would give me a total integral value of 3. C then wants me to do the integral from -1 to 1 for 2 times f of x plus 3 times h of x. So this one uses the constant multiple rule and the sum and difference rule. So the 2 and the 3 you can kind of pull out separate from the functions, and we can separate the order of, or the process of integrating them. So this would be like 2 times the integral from -1 to 1 for f of x plus 3 times the integral from -1 to 1 for h of x. And I know I left my dx's off, but I don't have a ton of room there, so I was trying to scrunch it in. So -1 to 1 for f of x is 5, and -1 to 1 for h of x is 7. So then it's just a matter of doing the math, and your final answer would be 31. All right, so then D wants the integral from 0 to 1 for f of x. So I'm looking up at the top. I see -1 to 1. I see 1 to 4. I do not see any zeros up there for f of x. Now, what some people might be tempted to say is that, well, 0 to 1 is half the distance as -1 to 1, so why can't I just take the -1 to 1 and cut it in half, because it's half the distance? Well, that would only be acceptable to do if you knew for a fact that this interval from -1 to 1 was symmetric about x equals 0, like it was a mirror image graph, or for example, something like this, where you would know that this amount of area was exactly equal to this amount of area. But I have no idea what this f of x graph looks like, so I don't know that it's symmetric like that. So I do not have enough information to answer D. E then is kind of along the same lines. We're going from -2 to 2 for h of x, but the only information we have for h of x is -1 to 1. So people might want to double it because the width is twice as big. But again, we don't know what the rest of the graph looks like, so we don't have enough information to calculate that integral. And then for f, we want -1 to 4 for f of x plus h of x. Well, if I use what I did on C and I separate those, I know from B that the integral from -1 to 4 for f of x is a positive 3. What I don't know is the integral from -1 to 4 for h of x. And again, I have no way of finding it because I only have information for -1 to positive 1 for h of x. So since I'm not able to find that, this one as well would be not enough information there. All right, so those are all of our rules for using integrals. The last thing we're going to talk about is the mean value theorem with integrals rather than the mean value theorem with derivatives, which we have already learned. So mean value with integrals, you're going to hear in the problem, find the average value of the function. Not the average rate of change, the average value of the function. And if you do that, the average value is found using this formula right here. You're going to integrate the function from a to b, but then you're going to multiply it by 1 over b minus a. Okay? It's very important that you remember that 1 over b minus a. So I'm going to show you an example here. We want to find the average value of the function f of x equals 3x squared plus 1 on the interval from -3 to 3. And your paper should have a picture drawn on it. I don't know why my picture got deleted. I see the box there, but I do not see the picture. But we'll worry about the picture in a minute. So I'm going to use my formula exactly. My integral is going to go from -3 to 3 for the function 3x squared plus 1. But since they want average value, I have to stick 1 over b minus a in front. So 1 over 3 minus -3. So that's going to become 1/6, and then I'm going to multiply that times this integral once I evaluate it. So remember, the 3x squared plus 1, that integrand is the derivative. So I have to think backwards to what did it come from. So 3x squared came from x cubed. The plus 1 came from x, and my boundaries are -3 to 3. So remember the way we evaluate that, we plug the upper boundary in first, minus the lower boundary. So we end up with 1/6 times 27 plus 3. That's a -27 minus 3, so a -30, but it's a minus right here. So that becomes a plus 30. So we get 1/6 of 60, which is 10. So what does that 10 represent? Well, what that 10 represents is that is the average y value of my function 3x squared plus 1 on the interval from -3 to +3. So if I want to, and then it says find all the x values in the interval for which the function is equal to the average value. So we want to actually find where does my function actually equal that amount. So you would take your function and set it equal to 10 and then solve for x. So that's going to happen at x equals both positive and the negative square root of 3. Both of which of those numbers are in my interval, so it's okay to keep those answer choices. So let me real quick just kind of sketch my picture here. And that should go all the way up to 28. So that's what the picture looks like on your paper from -3 to +3 at 3x squared plus 1. So let me show you where this 10 comes in. So if I go up to a y value of 10, that would be roughly about right here. And if I make a rectangle that is as tall as my average value and as wide as my interval, guess what? The amount of area in that blue rectangle is the same as the amount of area under my red curve, my 3x squared plus 1. And does anybody want to guess where these 2 points are? This is at the x coordinate of negative square root of 3, and this is at the x coordinate of positive square root of 3, because that's where my function is actually equal to 10. So this wraps it all up for you.